Hello everyone, welcome back to another SLHL IB chemistry video. Today we will be looking at structure 3.2, naming organic compounds and looking at functional groups. So before we do this, let's just define what an organic compound is. So an organic compound will often look a little something like this. So this here would be ethane. So organic compounds, essentially, right, are hydrocarbon chains in which carbons are covalently bonded to other elements, oftentimes being nitrogen, hydrogen, or oxygen. Now, over here, as I stated, we have the display formula for ethane. So the display formula is when you draw out every single bond between all of the elements. A molecular formula is one that demonstrates all of the atoms within a molecule. So that would be C2H6 in this case. The empirical formula is the most simple ratio of elements within a compound. So that would look like CH3 in this example. Next up, we have our general formula, which, as we have a alkane present, alkanes are hydrocarbon chains without double bonds within the carbons. There are none, meaning that it is saturated, no double bonds between the carbons, unsaturated, double bonds present between the carbons. So our general formula would look something like this: CnH2n plus 2, because that's simply the general formula for any alkane. Now, what are we missing? We have display, molecular, empirical, general, structural. So the structural formula is essentially the written out version of your display formula. So for this specific compound, that would look like this, representing both of our CH3s in our ethane. And finally, we have skeletal. So the skeletal formula, let's do propane instead of ethane, because it simply is a little bit easier to visualize. So in your skeletal formula, you use lines to represent the bonds between elements, and at the end of each line, or at every bend of the line, those points represent a carbon. So propane will be 3 carbons, meaning that we have 1, 2, 3. That is the skeletal formula for propane. And the assumption in skeletal formula for these hydrocarbons, or hydrocarbon chains, is that for every remaining bond that can be made, because carbon can make 4 bonds, that there is a hydrogen bonded onto those carbons. So this is quite a simple demonstration of what a skeletal formula can look like, but you can also have different structural isomers, which, as stated here, are molecules with the same molecular formula but different connectives, in which you have branching of our skeletal formula. So let's take that is let's take this as our example. So when it comes to naming these, we always have to look at the longest carbon chain first, and this is called the parent chain. This will serve as the basis of our name, and it is based on this that we put our numbers into all of our branches. So we have a 1, 2, 3, 4, 5, telling us that we have pentane at the end, and we always count from the side, which will give us the smallest number. So this branch here, you could say, you would be wrong, but you could say 1, 2, 3, 4. Oh, it's on the 4th carbon. But in reality, if we were to count from the other end, 1, 2, we could say that it is on our 2nd carbon, this methyl branch. And one of the IUPAC naming rules is that we want to keep these numbers as small as possible, just to keep things as simple as they can be, because with all these lines, with more lines and more lines, it can all get quite complex. And when it comes to naming alkanes based on their skeletal formula that have more than one branch coming off the same carbon, such as, for example, first we identify our parent chain. So our longest chain will be this one over here. And we have 1, 2, 3, 4, 5, 6 edges, or corners, sorry, which means that it will be hexane. Now, we'll start counting from our left to identify this chain to keep that number as small as possible. So 1, 2, that is our smallest number possible. And we have methyl little bits sticking out at our 2nd carbon. So we will say 2, 2, dimethyl. 1, 2, 3, our 3rd carbon, we have a ethyl sticking out here, so we will say that this is 3 ethyl 2,2-dimethyl hexane. Now, something to keep in mind when naming compounds are the IUPAC nomenclature, which is essentially a set of rules that chemists use, and they are used by the International Union of Pure and Applied Chemistry, just for, a more applied, systematic naming system, so that people name the same compounds in the same way. Now, as I was stating earlier, when we have an alkene or a double bond present in our carbon chain, what we do is that we add an extra line to represent the location of the double bond. Now, if we were to have this compound over here, we would refer to it as 2, 2, because both of our branches are on that 2nd carbon. You prioritize your alkene. And this would be dimethyl methyl. Hexane is our parent chain, so hex. And then 1, because our double bond is present on our first carbon, so hex 1 ene. Now, just taking a quick look at halogenoalkanes and how to name compounds that have halogens in them. So for our halogenoalkanes, your prefix comes from your halogen. So that would be fluoro for fluorine, chloro for chlorine, bromo for bromine, iodo for iodine, so on and so forth. So if you were to have an organic compound like this one, oh, that's an H up there, we would call this 1,2-dibromoethane. We use the numbers 1, 2 because 1 is on our first carbon and the other is on our second carbon, and ethane because this is a 2-carbon long chain. Let's get into our functional groups and what these look like, how to identify them, their suffixes when it comes to writing down their names, everything we need to know about them. So first off, let's look at alkynes. So an alkyne will be a chain in which a triple bond is present between your carbons. So that would look a little something, or could look a little something like this. And this is ethyne. And the functional group of an alkyne is alkyne, and your suffix will be YNE. Now let's look at alcohols. Your suffix will just be ol. And you know that you have alcohol on your hands when your structural formula presents a hydroxyl group, or essentially when you see OH onto there, and this is ethanol. Next up, we have different types of alcohol. So there are 3 main types of alcohol. There are primary, secondary, and tertiary alcohols, and these all have to do with the amount of carbons bonded onto the carbon that has the hydroxyl group on it. So a primary alcohol is one where you only have 1 carbon bonded onto the one with your hydroxyl group. A secondary one is one in which you have 2 carbons bonded onto the one with the hydroxyl group. And, quite self-explanatory, tertiary structure for an alcohol would look a little something like this. Now moving on to ethers. So before we get into this, we're going to introduce a new letter in terms of formula, which is R. Now R is simply any carbon-containing group. So an ether will look a little something like this. Here, this little dash up here is just to tell us that this carbon group can be different to this one. They can be the same, but they can also be different. So essentially, this is when you have an oxygen present in the middle of your carbon chain. An example of this would be, let's pretend we have hydrogens bonded onto all of those dashes. And this over here would be methoxyl methane. So suffix oxyl. Furthermore, we have aldehydes. These have a suffix of al, and essentially an aldehyde is identifiable by a double bond to an oxygen from a carbon, which is also bonded onto a hydrogen. And these you will tend to find at the ends of your carbon chains, because you can't really bond any more carbons in that sort of direction. Next up, we have our ketones, which are actually quite similar to our aldehydes, except that instead of hydrogen, we have another carbon-containing group. And these will often be found more in the middle of your chains. So these will have a suffix of -one, and these are carbonyl functional groups. The functional group of an aldehyde is simply aldehyde. And as we said earlier, ketone is just an aldehyde without a bond to an oxygen. And next up, we have esters, which have a suffix of -08. And these will look a little something like this. We do have a carbon here in the middle. I'm just not going to draw out every carbon, or else this video is never going to end. Now, typically, you will see esters when you have a carboxylic acid. So carboxylic acid. Let's draw out what that looks like real quickly. When you have a carboxylic acid that reacts with an alcohol, creating a condensation reaction, you will get your esters. Now, esters, fun fact, are actually known for smelling quite nicely. Smelling quite nice. And in terms of our condensation reactions, if we want to look at an example of that, we can think of a condensation reaction between two glucose molecules giving us one maltose, which at its very center, you will see a ester connecting the two together. An example that you will probably be quite familiar with if you study biology. Going on to our carboxylic acids, this is what they're going to look like. Examples would be ethanoic acid or fatty acids, or essentially organic acids. Maybe think of your triglycerides. And in terms of the IUPAC naming rules in reference to carboxylic acids, so when you see a carboxylic acid present in your compound, do start your counting from this acid, as it does take priority. Now, as it is, as we said, an acid, do keep in mind that this will be a proton donor in chemical reactions. Next up, we have our amines with a suffix of amino, just like amino acids. Did we mention? We did not mention carboxylic acids have a suffix of oic acid. So this would be like propanoic acid, for example. Now back to our amines, amino, and this will be when you have NH2 bonded onto a carbon group. And yeah, that's essentially what it will look like. A good example of these are amino acids, in which you have your NH2 bonded onto a carbon, which can have any R group bonded onto that. Next up, similar to, but not the same as amines, we have amides. Now these two can be quite easy to confuse, as they both contain our NH2 groups, but what makes them different is that an amide will have a oxygen double bonded to your carbon that's bonded to the N, whereas your amine does not have any oxygen present. And the suffix for this is also quite different. It's carboxamide, because you have your carbon and your oxygen. Next up, we have our nitriles, which look like this. Essentially, when you have a carbon that has a triple bond to a nitrogen, and an example, a very popular example of these would be cyanide. And next up, actually before we go on to that, that will be a suffix of cyano. And finally, for our functional groups, we have our arenes. These have a suffix of phenyl, so those are phenyl groups, and they present one of two, not structures, but ways of drawing their structure. Because you can either have that on the left or this on the right. They mean the same thing. Now these can oftentimes also be referred to as aromatics. So let's write that down. Aromatics. Now when it comes to your functional groups, memorizing their names, the actual functional group itself, and what they look like, it's simply practice. You just got to go over these again and again. A nice way to do these is through the use of flashcards, or for example, looking up images of large compounds online and trying to circle all the different functional groups that you can see, and just doing this over and over again until they get into your head. Let's just quickly look at a homologous series and what exactly this word means, because we will have to know about these. So a homologous series is a series of compounds in which all the compounds present the same functional groups and similar chemical properties. And the differences between the different compounds in this series is often simply the length of their parent carbon chain. Successive members of a homologous series show a trend in physical properties. And that is that as the MR, or the relative molecular mass, as this increases, so does the boiling or the melting point of that compound. So you might get a multiple choice question in which you're asked, which one of these compounds will have the highest melting point? These will be of the same homologous series, and this is when you will have to find the one with the largest MR, because these will be the ones with the highest melting and boiling points. Next up, we've already, in fact, used these, but we haven't actually looked into what exactly these are, which is a structural isomer. This has to do with for example, earlier in our skeletal structures, when we had branched chains, or our secondary and tertiary alcohols. This also involves our halogenoalkanes, in which we have halogens bonded onto our alkanes, and our amines, in which we have a nitrogen in there. Now that is all for structure 3.2. Hope that was helpful.